Okay, good afternoon, everybody. Welcome to 6333. Today we'll be finishing up our advanced topics on p-n junctions, and then we'll be covering the Schottky diode. The Schottky diode, what you're going to see in the Schottky diode is it's going to be deja vu to the p-n junction. Okay, we're going to really take a very similar approach, and we're going to see a lot of similarities between the two. But then we're also going to understand how they're different. So I want to thank Shini and the rest of the class for making this video recording possible so that you guys could watch this lecture in your pajamas. Now, before I go into the technical content, I do want to boast that one random person on the internet said I should put more lectures up there. Just one person. I got one comment, and so I was really inspired by that random person. So this is for you, random person. This lecture is for you. I dedicate it to you. Okay, so where we ended last time is we were talking about if we had non-uniform doping in p-n diode, how would it qualitatively change the situation? And we can only really answer qualitatively. If we want to answer quantitatively, we need to run a computer simulation. So what's shown here are two different doping profiles. And this one, this is the edge of the depletion region. This is the edge of the P side where the diode ends. And once again, this is the edge of the depletion region. So we're only showing the P side. Okay? We're only showing this P side of a p-n junction. But what we're trying to show here is if the NA concentration was upward sloping like this, and remember the junction's over here, well, due to non-uniform doping, we're going to have diffusion of carriers, right? And so carriers are going to diffuse from where to where? From high concentration to low concentration. So that's what you see. So they diffuse, non-uniform doping, that creates an electric field. What direction is this electric field in? Well, we have a net negative charge here, a net positive charge here. That creates an electric field this way. Okay? What that means is these, now when we inject a minority carrier on the P side, not only is its velocity going to be its diffusion velocity, but it's going to have an additional component due to drift. So before we assumed the quasi-neutral regions were quasi-neutral, that there was very little electric field there. Now there could be a small electric field. And in this case, if my minority carriers are diffusing this way, that electric field, that puts a force on electrons this way, so it increases the diffusion of electrons. Well, how is it? It's not really increasing the diffusivity, it's just putting an electric field in the direction of diffusion, which overall makes it look like I have faster diffusion. I have a faster effective diffusion velocity. Does that make sense? Conversely, if I had a profile like this, all my profiles are going down to 0 at the junction, because if my profile was still going up like this, then I wouldn't have a p-n junction. I would just have a P region with non-uniform doping. So this is I'm just showing the P side to keep it simple, but you can imagine there's an N side abutting it. Now in this one, I just have a downward sloping profile. It gives me an electric field in the opposite direction. That electric field is going to oppose, so electrons are negatively charged. That's going to put a force on the electrons in the other one. That's going to oppose diffusion. Okay? That's the qualitative picture. Any questions about that? Okay, so the next topic is important. All these topics are important, but I want to discuss breakdown voltage in a diode. Who here thinks breakdown is bad? Yeah, it sounds bad. I just want to caution you, it doesn't always have to be bad, but it could be bad. So what's happening here? This is the forward bias part of the curve right here. And this is a really large scale, so all we're trying to see is, okay, the current is increasing exponentially in forward bias, it's just increasing so much it goes off the scale. In reverse bias, the current's very, very small. But at a large enough reverse bias, breakdown happens. Now you can design diodes intentionally to have this breakdown. And you can use this as an advantageous feature. Anybody have an idea what I could use this for? This breakdown? What was that? A regulator. Yeah, so switch, maybe, but with the switch we typically need like 3 terminals. You know, in a typical switch, but a regulator, right? So here, if you're operating in this regime, your voltage is really fixed. You can't really change voltage from here. So this could be used in some regulation circuits. Now, of course, when you want to use this, your current is increasing really quickly, you know, in both forward bias and reverse bias. If you let that current increase to whatever you want, well, you're going to burn up your device, it's going to die, you're going to start burning plastic if you're using discrete components. If you haven't had that opportunity in your life to burn a discrete component, you should play more around with discrete components and max them out. But this diode might be rated for some max current. So what if I took this device, right? Let's say it was rated for 1 amp. That was the max current that this diode was rated at. That's what it was designed to handle without burning up. Okay? If I put a 1 ohm resistor in series with it, or it depends on, let me back away from that statement a second. If I know what my max voltage will be, right? So let's say the max voltage I want to apply might be minus 10 volts. If I put, in that case, a 10 ohm resistor in series with this diode, then 10 volts, assuming the diode is fully conductive, then 10 volts divided by 10 ohms gives me 1 amp. So it would keep me, from exceeding my max current rate. And 10 ohms doesn't sound like a lot of resistance. Well, it depends on your application. But you could design this in such a way that you could have a lot of current flowing, but it wouldn't increase to infinity, right? Does that make sense? I'm not giving you the full circuit application. I'm just trying to say, well, this doesn't have to be catastrophic. It will be catastrophic if you let the current go to infinity, because then things are going to melt. But if you don't let that happen, it doesn't have to be catastrophic. It can actually be a phenomenon that we understand and can control. Okay? So depending on your application, this can either be a parasitic effect or an advantageous effect. You can design your whole application around this, or you could design your whole application to avoid this region. Just depends what you're trying to do with your diode. A diode can do more than just one thing. Okay? So in most PN diodes, this breakdown region here is due to our favorite phenomenon, because it's the coolest phenomenon we can talk about. It's avalanche breakdown. Somebody remind me what avalanche breakdown is? Why is it called avalanche breakdown?
Because the one carrier is going to, triggering the emission of a function.
Yeah, exactly. So I have a high field region. Why? I know I have a high field region. I'm going to a high bias, and it's called avalanche because it's a snowball effect, right? I have one carrier. It gains a lot of kinetic energy. It has to gain kinetic energy equal to the band gap, at least equal to the band gap. It collides with the lattice. It loses its energy, but in the process, it breaks a bond, creates an electron hole pair. these two electron hole pairs can go and gain energy, collide with the lattice. Those two can now create 4. And this hole is going this way and can do the same thing. Okay? And so it's a snowball effect. It's an avalanche. You know, a small piece of snow keeps, maybe some of you are from warm climates, maybe some of you are from cold climates. Hopefully nobody's been in an avalanche, but right? A small little piece of snow creates a bigger and bigger snowfall, right? Until the whole, that's why it's called avalanche. And because it's the coolest thing we can name it after, right? This is the coolest you can be as a device engineer, talking about avalanche. Okay? So, avalanche goes with the electric field. The larger the electric field, the more likely the carrier will gain enough kinetic energy before scattering. If the electric field is small, then yeah, the carrier will travel some distance and maybe gain some kinetic energy, but then it will scatter, and that kinetic energy won't be enough to create an electron hole pair. Okay? So when the reverse bias gets large, the electric field gets large across the junction, and the multiplication constant increases. And you'll have a homework problem on this. When you want to take this into account very accurately, it becomes quite involved. Well, why is that? Well, avalanche depends exponentially on the electric field. And the electric field is not constant across the junction. And so you can go and look in that. And this is a chart for silicon. This is only valid for silicon. Why? Well, because it's going to be different when you have different band gaps and different scattering times. And this is showing for different doping levels, you get different breakdown fields. Well, why do you think you have a larger breakdown field at higher doping? Why do you have a lower breakdown voltage at a higher doping?
Because in the higher doping, you got more possible snow voltage to be triggered.
Not so. I understand your point, but remember the snowball is actually what is actually avalanching. It should be I would think of it as a minority carrier in the depletion region, right? So weirdly, right, the higher the concentration of doping is on both sides, the lower the concentration of the minority carriers are. But yeah, you have a higher field, right? So even at zero bias, the higher your doping is, the higher the electric field, right? Phi BI is staying about the same for these devices. Yeah, it might change by a little bit, but it's around 0.7 for silicon. But the depletion width is very, very different, right? The depletion width, I think, goes as the square root of the doping if it's the light doping on the lightly doped side. So if your doping changes, by 100x, your depletion width changes by 10x. That's going to really reduce your electric field. You have to drop the same voltage, across 10 times longer, your electric field's going to go down. But what you're saying is not completely wrong. I'd have to think about that a little bit more.
It seems that I'm always asking such open questions.
Because you would have, right at the edge, this is what I'm trying to say to your question, or your response, is that, from the P region, right? The P region is injecting into the depletion region, right? Well, typically we don't think about the injection into the depletion region. We're thinking about the injection of holes into the N region, right? So we're not really even considering what's happening in the depletion region, right? That was our simple approximation. So it may not be completely wrong. I'm just, I'd have to think about that a little bit more. Okay. Another thing with diodes, another non-ideality is series resistance. So far we have assumed if we apply some voltage across the junction, or some voltage across the diode, all of it appears across the junction. Well, let's assume I have very long quasi-neutral regions. They have some finite resistance to them. And so for them to carry some current, some voltage has to be dropped across them. They're not infinitely conductive. Now, if your junction, you have to think about it as series resistors. And keep in mind, the effective resistance of your junction is changing as a function of voltage. Right? You got your junction, that's what we've been studying so far in a p-n junction. Its resistance is dynamic. How do we know that? If we plot I versus V, where V is the junction voltage, is that linear? No, it's this exponential of QV over KT minus 1. Okay? And so the effective resistance, right? If I just calculate the resistance as I over V, that's changing as a function of voltage. And so initially that is quite small. I mean, that resistance, the opposite of what I said. Initially, the resistance is quite large. How can I see that it's quite large? Well, the slope here, so this is supposed to cross 0, but the slope near voltage equals 0, V versus I should be very explicit. This is my V exactly across my junction, assuming no voltage drop across my quasi-neutral regions. My slope here is very shallow, and that corresponds to a large resistance. You can think about that. If I had a really large resistance, then I change my voltage a lot, and my current is very small. Okay, so initially my junction is very resistive. So even if my quasi-neutral regions have some finite resistance, probably my junction overwhelms it, and we can just ignore them. But in strong forward bias, my junction resistance is dropping very, very quickly. And it may not be the highest resistive element in this series combination. So we can actually deal with this quite simply if we just assume that the other resistances, we just lump them all together and we just call it RS. RS is standing for series resistance. It's just some resistance in series with it. It could be due to the quasi-neutral regions, it could be due to the contacts, it could be due to other elements, the wires connecting. And so what that means is, what's the voltage? If my diode is conducting some current I, what is the voltage drop across all those series resistors if their series resistance is RS? What? IRS, right? So if I apply some V, before we assumed that all of the V appears across the junction. No, now if I apply V across my device, and that gives me some current, well, the part that actually shows up across my junction is V minus IRS, because IRS is the voltage drop across my series resistor. And this is assuming I'm getting some current, in my device, right? And so this is my effective voltage across my junction. So I just plug it into my diode equation, and it's perfectly fine. Now, don't get confused. IS is different than RS. IS is not the current going through the series resistor. That's the saturation current, okay? RS is the series resistance. Sorry, they look similar. Okay, but this is just the effective voltage across my device. Now, what do you notice about this equation? Is this equation easy to solve? It's transcendental, right? An exponential of something, I, V minus some I, is equal to I. So how do you solve that? Well, you can iterate. You could, there's a lot of numerical techniques that you can use, okay? So you can look for intersections, right? So you can plot this half and then this half for a constant I. You can see where they intersect, right? That's the voltage that you have to apply, right? You plot this, you say what voltage do I have to apply to get 1 milliamp out of this device? Well, you know everything except you don't, 1 milliamp, right? So then you know this, so you can plot this side. But if you know the current, then you can just plug it in, and then you only have one variable and you can solve it. So what does this do? Okay. So this really only impacts the curve. It's better to look at the log scale here. Here, nominally, my device is increasing exponentially, 60 millivolts per decade, and this is a perfectly straight line on a log scale. Because exponential on a semi-log scale looks like a straight line. Or, yeah, straight. Okay. This IRS, that voltage drop across my series resistor, if RS is 0, then I have 0 voltage drop across that, and I move back to this line. As my RS becomes larger and larger and larger, it's going to bend my curve more and more. Why? Because now I have to apply a larger voltage. Okay. And so we can be a little more rigorous with this and break that series resistance up into the contact resistance. We're about to get there, top and bottom contact resistance, and then into the resistances RCP, RCN, contact resistances of the P and N side, and then RP and RN are just resistances of the quasi-neutral regions. Okay, well, what's the resistance of a quasi-neutral region? Well, here we're assuming it's uniformly doped at Na, and we already know how to do this. We have a semiconductor bar. It's uniformly doped, some length, it's some width, some thickness. What's the resistance? Yeah. Right? Remember, R is equal to the resistivity times the length over the width of the device times the thickness of the device, which in this case is just equal to the area. This is the length. This is it. Woo! That was exciting. And this bar has some resistivity. Right? Resistivity is in a weird unit of ohm centimeters, or ohm distance. Why? Well, you can see when you put it all together, ohm centimeter squared divided by centimeter squared gives me ohms. Okay, resistivity is a material property. Resistance is not. I can change the resistance of a material by just cutting it differently. I don't change, assuming it's a uniformly doped material, I don't change its resistivity. Resistivity is more general. So that's the length, WP minus XP. That's the resistivity, 1 over Q mu H in A. That's actually, this thing right here is actually a conductivity. 1 over the conductivity is the resistivity. And there's my A. And then I'm just adding it for both sides. Okay. And then in the interest of time, I just want to launch in to the Schottky diode. Okay? So as I said earlier, a Schottky diode, this is where the class, this class is always been fun. Let's not kid ourselves, right? This is the best class you're taking. But we start to take these concepts and we start to get to reuse some things. We're going to start to feel like we are masters of this content, and hopefully some of this seems easy at this point because you've already done this maybe a couple of times already. Okay? Now, why are we even covering it if it's so similar? Well, there's a key difference. And the key difference with the Schottky diode, which is a metal semiconductor diode, compared to a PN diode, which is a semiconductor diode, is that we're going to see that the injection in the Schottky diode is going to be of majority carriers. We're a little premature to understand that just at this second, but that's what we're going to see. And because it's a majority carrier device, well, it's going to have different behavior as compared to a minority carrier. Now, all the behavior of the device isn't going to be different. Its switching characteristics are going to be different. Okay? And so Schottky diodes are really fast. PN diodes are not super fast. And remember, fast, we're talking about picoseconds. Under nanoseconds, right? In the world of electronics, a gigahertz is already kind of slow now, right? A gigahertz is 1 nanosecond, right? If you want to have a really fast device, RF, in analog, you know, it needs to be much, much faster. Its intrinsic speed needs to be much, much faster than what you're using it at. So these devices can be super fast because they don't have minority carriers in them, right? In the diode, you have these minority carriers that have to decay. You inject some minority carriers in your device, or you extract some minority carriers from your device, and you want to bring it back, well, it's going to take you some time. Because those minority carriers don't recombine instantaneously. If it's a majority carrier, we can pull those carriers out very quickly through the contact. Okay? Schottky diodes are diodes. They have rectifying characteristics, but they're majority carrier devices with fast switching. Okay? So here, I hope this looks similar to the PN diode. This P region's not there to confuse you. It's just on a bulk wafer. It's always doped to something. And so the device of interest is just right here. It's this metal semiconductor junction. This is just a contact. This effectively is a contact to the backside here. And this P region here isolates this from other devices. Why? Because you should already see a PN junction can rectify, right? It provides a barrier to current flow. If I forward bias this PN junction, can it conduct? Yes, it can, if I forward bias it. So we better not forward bias this PN junction. Keep that in mind, right? And that's how we would design our circuits. We could never have it where this PN junction's forward biased. But as long as we keep this neutral or reverse bias, we're fine. And remember, we've got an effective contact here, right? In this M+ region, this is making a really good contact. And so this contact is effectively controlling the potential of the device. And so it's just like a 1D device like this. Or here's a metal semiconductor junction, and this is, imagine this, you know, it's kind of coming down and it's effectively a contact at the bottom. Okay. Why does it look like that? Because we have to make everything from the top. And this doesn't have to be as big of an area because it's much more conductive, because it's got an M+ region. So at the end of this topic, we're going to discuss ohmic contacts, okay, which are, we're going to see, so when we take a metal semiconductor junction, and instead of having it rectify, we're going to want it to conduct as much as possible, so that whether we apply forward bias or reverse bias across it, so much current flows that even if it kind of rectifies in one direction or another, it's so much more conductive than the rest of the circuit or the rest of the device that that part dominates, and the contact is just the contact. Okay? So here's our ideal Schottky diode. Okay, we're making all these approximations. Many of these approximations are similar to what we did before with the PN junction. We're going to make it 1D. Okay, and we're only going to study this top half. We're going to assume this one an ohmic contact. Another way to say that is this is a perfect contact. We're not going to make it more difficult on ourselves when we're studying a new junction. Let's not study two of them at once. Let's study one of them at once. Okay? We're going to assume uniform doping. We're going to, there's going to be some parameter called the Schottky barrier height. We're going to tell you how to determine that based on the metal work function minus the electron affinity of the semiconductor. The band alignment, okay, between the metal and the semiconductor is going to produce a depletion region at 0 bias across the device. We're going to use the depletion approximation. Oh, we know how to do that with P diodes. We're going to ignore minority carriers, ignore parasitic resistance, assume ideal only contact at the back, and assume no edge effects. Okay, that's a lot of assumptions, right? And we came in with P and diode, and we addressed some of these, but then some of them, you know, we can't fully address in an analytical model. Okay? Nonetheless, what we do is very indicative of understanding how real devices work. Okay, so this is how we understand these devices, okay? Now before I make a junction between a metal and a semiconductor, I'm going to make a metal-metal junction. Okay, so the metals have different work functions. Work function is from the highest, it's from the Fermi level to the local vacuum level. Okay, these two metals, okay, there's other bands that are filled or not. And remember, a metal, the band doesn't end just right there. The band, you know, there's more states, but that's where the Fermi level is. Okay, the Fermi level's in a band in a metal. Okay. And there's other bands below it, but we don't really care that, right? So these materials are apart. Boom, we bring them together. This is our thought experiment. And what's going to happen? Well, the Fermi levels aren't equal, so they're not going to be in equilibrium with each other. So we're going to have a transfer from higher energy to lower energy. Now, what happens when electrons leave this metal? Did this metal come in charged? So when negative charged particles come off of it, what's going to happen here? It's going to leave behind a positive charge. That's going to set up an electric field. That's going to change the effective potential across the junction. There's going to be band bending, and that electric field is ultimately going to stop diffusion at some point. All of the electrons don't flow all the way. If this was water, they would. Right? I have water, two different levels. I bring them together. I let them communicate. Water's going to flow from the higher level to lower level until they reach the same. Here, I have the exact same thing. Electrons flow. But the difference is electrons flow, you can imagine it just like water, but as they're flowing, they're leaving behind charged particles that are going to stop, reduce that flow until that flow goes to zero. And that sets up this electric field. Now, the band offsets maintain. So if I had this much of a band offset, then I'm still going to have that. If I had the offset from here to here, that's a material property. These are all to the same reference, right? And so I'm still going to maintain that offset. Now with a metal, I can't have charge in the bulk of a metal, right? There's too many carriers to screen it out. So what I get is in a metal, I'm going to have a dipole of charge right at that interface. And so this is going to be very, very narrow. It's shown to be big here, but it's a picture. It's going to be very, very small. But it's going to produce a substantial electric field. A substantial built-in potential, or whatever it was originally. So that must mean my charge dipole is quite large, because it's over a very small distance. Now, I discussed the local vacuum level before. And the local vacuum level is, I'm taking an electron out of my semiconductor and putting it right at the surface of my device. I'm not moving it infinitely far away. I'm just pulling out that electron and putting it right on the surface. So there's a dipole here. So if I move this electron, if I pull this electron off and I put it right on the surface, and I slide this electron across my device, it's gonna feel that potential. It's gonna see that dipole. And it's gonna have to work to get through that dipole. So that the local vacuum level does change. Another way to say it is, if I took an electron and I pulled it off this side, this dipole is going to, so as if my electron came over here and it came across that dipole, it would gain kinetic energy. Conversely, if I pulled an electron up here and I wanted to move it across the dipole, I would have to give it energy to cross that. Why? Because the dipole opposes the electron flow across it. In this case, the dipole, well, I'm going to have electrons going here, so it's going to be a negative charge on this side and a positive charge on this side. And our dipoles close together, so I only feel that field, negative, positive. The field is this way, which causes the electron to go that way. That's the local vacuum level. Okay, and the local vacuum level, the reason why it's useful is it exactly mirrors the potential. If I look at my local vacuum level, I can see the potential across my device. My potential is just the negative of the change of that. Why? Because these are energies for electrons are negative Q phi, where phi is my electrostatic potential. Okay? So for this metal-metal junction, my rho, my net volume charge, would look something like this. That would give me an electric field that way. I hope I said that correctly earlier, right? That electric field in this scale is negative, so we're going to see it dip down like that. Okay, everywhere my electric field is negative, right? Here's my potential, it's the integration of my electric field with a negative in front of it. Electrostatic potential and then potential energy for an electron, right? It's going to be like this. Well, what we know is that phi bi, the total potential difference across the structure has to equal phi bi. Or the total energy change in the potential energy has to be Q phi bi. Why? Because that's how much these bands had to move by to be aligned. Because this is phi bi. Phi bi is just the difference in these work functions. So for me to reach equilibrium, I have to have something that gives me the band bending equal to phi bi. In a metal, the extent of the space charge region is a fraction of a nanometer, right? That's the standard saying that we say, charge on a metal exists only on its surface, right? That's that saying. Why? Because there's just so much charge, there's so many electrons. Yeah, there's a sea of electrons in a metal that it can't exist in the bulk because the electrons will swarm around it and cancel it out. Okay? So this is a local work function. Local work function, okay, is if I had a material like this, I shone light on it, it's whatever light it would take to knock an electron up from the Fermi level Fermi level off outside the material. Okay. and the average location of an electron is going to be at the Fermi, right? In a semiconductor, we don't actually have states at the Fermi level, but that's kind of the average location that I would add an electron, if you think about it, right? In a neutral semiconductor, I would on average add either in the valence band or in the conduction band. So the Fermi level's in the middle of the band. Okay, now when this work function is smaller, well then I need a smaller energy to knock an electron off, right? I can send them a laser. Now across this junction, it actually changes, which is kind of neat. Oh, sorry. Yes, it does change, sorry. And this is what we call this local work function. This is this local vacuum energy that I described. It's the energy right above the surface of the semiconductor, right? Just where I had a free electron right above the surface. Why is it not flat? Because you're right above the surface. And so you can see the dipole that's underneath of it. If you defined your local vacuum level, at infinity, well then sure, all that charge is going to cancel out and that's going to be flat. But then it's not that useful. Because we're typically never taking the electron to infinity. Okay, so now let's do the ideal metal semiconductor junction and thermal equilibrium. Okay, so here's what we have. We have our metal here with a work function Wn, and we have our semiconductor here with a work function Ws and electron affinity chi. Okay. Chi is the energy from the conduction band edge to the vacuum level. And here, Q phi n is just this distance. And it's defined as just EC minus EF. Why do we have that term? Well, we like to have as many terms as possible, right? That's our goal in this class. Okay, but we can see chi plus Q phi n is equal to W. And remember with Ws, the more positive, Ws is always defined as a positive quantity. All work functions are defined positive. So the larger the work function, the lower the Fermi level. Okay, so when I combine these, what's going to happen? I can see that they're not combined yet because they're not in thermal equilibrium with each other. They have different Fermi levels. When I push these together, what's going to happen? It's going to be flat. What type of charge transfer is going to happen? Well, there's higher. Yeah. The electrons on this material have a higher average energy. That's reflected in the Fermi level. So some electrons are going to move over from here to here. How many? I can't tell you. That's what's going to happen. And that's going to create an electric field that's going to lower this side with respect to that side. And that electric field is going to have to be enough to be equal to phi bi, or the integration of that electric field is going to lead to some potential drop across the structure, and we needed that potential drop to be equal to phi bi, right? This is a little bit different than a p-n junction, because this is if you like to think of it in such a way, it's a heterostructure. These are different materials. Hetero meaning different. The other ones you've looked at have been homostructures. It's just silicon-silicon. It's the same material. Yes, it's differently doped, but all the bands, there's no discontinuities. this is a material property, okay? This EC, this difference between EC and here, that's a material property. Another way to think about it is if I have two semiconductors with different conduction band energies compared to the vacuum, and I bring them together, well, there might be some band bending and stuff, but there's always going to be this discontinuity. I didn't somehow change my that's a property of like the crystals, right? The energy to get, and so I maintain that band discontinuity. And so here that band discontinuity, call it phi Bn. Now assuming the junction's perfect, assuming it's perfect, phi Bn is just the difference between EC and EF.
Why is it saying EF? Shouldn't be the difference between Fermi level here and there?
That's phi Bi, is the difference between the Fermi levels. So that's the total band bending that happens. So I put them together, and sure enough, I get a total bending of phi Bi. I can see that here, my local vacuum level bends by phi Bi. My conduction band here bends by phi Bi. And far away from the junction, EC minus EF, which we're calling Q phi N, it's the same as it was earlier, right? Far away from the junction, nothing should change. Sure enough, everything's the same. If you ignore this part, everything's the same far from the junction. But right here, I have a discontinuity. Well, we know we have a discontinuity. I'm going from bands in a semiconductor to, well, in a metal, our abstraction is we don't even think about bands because there's states everywhere. But this isn't the perfectly correct way to think about it, but if it's a tool to help you, then I'll let us be slightly incorrect in saying this, but you can use this as a tool. This isn't the truth. If you imagine this as EC of the metal, it's not EC of the metal, not at all. But if you imagine it, there's some discontinuity between the ECs. And that's different than phi Bi. And so that discontinuity between the ECs needs to maintain itself. In this case, it's not EC, it's the Fermi. Now, with the Fermi level, this is trying to show a zoomed in view right at this edge, and it's saying that there's very, very little potential drop on the metal side. You already know this, believe it or not, because when you solve the abrupt p-n junction, you saw that the potential drop on the, if it was an abrupt p plus n junction, you saw that there was very, very little potential drop on the p plus side. You can go back and look at that, and you can think about it, right? Well, how did we get that? Well, we had these types of band diagrams, or we had these rho electric field potential energy band diagrams, right? And we could see that it was really lopsided. You know, if this was a spike here, and this was a broad thing over here, you don't get much potential drop on the side with the spike. And indeed, you don't. For the metal, it basically is a spike right at the junction. Why is that? Well, once again, in metals, they only have charge at their surface, right? Where is that coming from? It's coming from the Debye length of a metal, right? Electric fields can't penetrate. Why can't they penetrate into a metal? Because I have so many free carriers in a metal that they just scream. And so going back to that analogy with the P plus in junction, you know, you can think of a metal as a P plus 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 junction, right? It's got a carrier density, I think, on the order of something ridiculous. Like basically in a metal, almost every atom in the metal gives up an electron. So it's around Avogadro's number of electrons in that C. It's not giving up an electron. I mean, the atoms are still there, but the electrons are all just in this C around the atoms. So, you know, how many atoms do I have in a mole? I have Avogadro's number, right? How many moles are in a cubic centimeter? On the order of 1, maybe on the order of 0.1, but around that, around Avogadro's number. And so I have around Avogadro's number of free electrons in metal. That's why metals are metal. That's why they're so conductive. Okay, so here's my band bending. Okay. And so this is this simple approximation. This is assuming a perfect junction. There's no idealities, no non-idealities. And it just says that phi Bn is this, EC minus EF on the metal side before joining, which I can also express as the work function of the metal minus chi of the semiconductor. But this falls apart if there's any non-idealities, if there's any defect states at that surface. And in fact, we typically don't get the barrier height. This is called the Schottky barrier height. Oh yeah, it looks like a barrier. Looks like a barrier to getting electrons into this device. This Schottky barrier type, and this is saying for an in region, because I have an in region here, it's a Schottky barrier height to the conduction band. Okay, I could also have Q phi P. What it's saying is it's saying that in practice, we look this up. You have to do an experiment and extract it and look it up. Or measure it yourself. But okay, if you want to be ideal and say, well, let me just get an idea. I know this number may not be exact, but okay, you can use this as just a guess. But it'll just be a guess. And we'll talk about this a little bit more later. So that's what this is saying, okay? So the typical Schottky barrier heights, silicon are quite large, 0.4 to 0.8. It's a really large barrier. That's a lot of 60 millivolts per decade. That's the useful thing about 60 millivolts per decade. You can take a barrier height, you can start thinking about it in terms of, well, how many electrons are there at 0.4? You know, I know how many electrons there are at 0.6, right? It's that's 10 60 millivolts. So that means I have 10 to the 10 fewer electrons at this point compared to my Fermi level. If that barrier height is 600 millielectrons. That's not perfectly right because I can't go all the way to the Fermi level because now I'm not purely at Maxwell-Boltzmann statistics. It gives you an order of magnitude, right? Okay, it's maybe 10 to the 9. Right? There's very few electrons that high above the Fermi level. Now, yeah. Now this is true. And you can see the geometric argument for it, right? Phi Bn plus phi Bi has to equal 5. It has to. And so this that is. Okay, so here we go. Now that was all talk. Now let's get into the mechanics of it. Okay? Electrostatics and thermal equilibrium. We're assuming that the metal, right? The metal could be anywhere, right? If the Fermi level of the metal was up here, electrons are going to transfer into the semiconductor. That's not going to create an electron barrier. But we're going to assume that the metal is down here with the Fermi level below that of my n-type semiconductor. That's going to deplete my semiconductor. So let me just say these things. Close to the metal semiconductor interface, I'm going to have a space charge region. Then further away, I have a quasi-neutral. Okay? So here's my picture of rho. I'm going to do the depletion approximation again. Now this time, the charge on the metal is basically a delta function. It's not exactly a delta function, it's some distribution with the width of the Debye length of the metal, which is less than a nanometer. But we're going to calculate everything from the right. Okay? So we don't need to know exactly what's going on in the metal. All we need to know is, well, these areas have to be equal and opposite. Okay? Well, you don't see that here because this is going to basically negative infinity, but the area of this spike has to be equal to the area of that. Remember, these could be 10 to the 5th difference. So if you're seeing that, it's all the way in the basement, maybe more. Okay, so then we're going to integrate this from the right side, get electric field. We're going to assume from some distance xd, we're going to have to calculate what that is. We're going to integrate from the right. That gives us max electric field at the junction, and then the electric field quickly goes back to 0 when we integrate over this spike. Why is that? Well, the total charge enclosed, when you're integrating, is 0 at that point, so there should be 0 electric field over here. Now, of course, when you're integrating this way, you gotta make sure all your signs are right and everything like that. What I typically do is, that hurts my head a little bit, so I just integrate because I know how to integrate, and I know I can figure out what the sign is by using my head as well. And then I don't have to keep all the signs in terms of the integration. I don't know. I don't know about your experience. I never really grew up integrating from right to left. And so, okay, it's not that big of a difference. It's just something a little bit different than you're used to, so you can kind of get some signs messed up. Right? Yeah, what I'm saying is you're integrating from, negative infinity. I mean, from infinity. Okay, and then we're going to integrate the electric field to get the potential. Integrating a straight line is going to give me a parabola. And then the electric field goes to 0, so then it's just flat here. I know that I choose, remember, with potential, I can always choose my reference. Here, since I'm integrating from the right to the left, I just choose my reference as 0. And it has to go to phi bi, right? In this case, minus phi bi if you follow the signs. And then from phi, I can draw my energy Venn diagrams. And from my energy Venn diagrams, I can draw P naught in it. And I'm putting that on the log scale, right, because they're changing very quickly. Okay, these are the equations. They're not really scary. We know what we're doing, right? If we understand this, we can get those equations. But those are the equations. Not something worth memorizing, but that's what they work out to be. Okay? And all this is in terms of XD, some parameter we don't know. We start off with a constant here. We're ignoring the metal side. We don't need to know the metal side. Yes?
So the previous graph, this is the depletion region assumption between the metal and semiconductor, right?
Yeah, we're assuming that we're solving the semiconductor region, assuming the depletion approximation. So the blue curve right here is like the exact, if I were to take the exact profile, but here I'm just making it a rectangle to make all my things easier, right? Overall, I should point out the depletion of region. It's definitely an approximation. Well, how do we know that? Well, we put in this square profile, and what do we get out? Right? So okay, look at the dashed line. That's the depletion approximation. Is this a perfect square? No, this is assuming all my carriers are depleted. Well, this doesn't look like a perfect square to me. But keep in mind, this is a log plot. So there's some tail, but you know, if 99% of my carriers are depleted, it basically looks like all my carriers are depleted. For 99% of my carriers to be depleted, or 0.01, 1/100th of my carriers to remain, how much must my potential have changed? It's kind of a convoluted question, but I said, how much does my potential have to change for my carrier concentration to go from 1 to 0.001? Looking at the back row, y'all got it. I see it in you. 120 millivolts. Okay? So my question was, well, when have all my carriers been depleted, right? So if I'm just making the numbers simple for me. Well, maybe I can consider them all depleted when I've gone from, if I had one carrier originally, to 0.01, you know, afterwards. That's 99% of them are gone. You know, if 99% of them are gone, well, maybe my height is Q and D, but this is at 99%. You know, you can't see it. Remember, this is a plot of rho, net volume charge density. So that's just showing the ionized donors behind that are positively charged. So all it takes for 99% to be, you know, for my carrier concentration to change by 100x, that's basically the question, is 120 millivolts. So if my, you know, after this moves 120 millivolts, 99% of my carriers are depleted. If I move it another 60 millivolts, okay, 99.9% of my carriers are depleted. I move it another 60 millivolts, 99.99% of my carriers are depleted. But from a point of view up here, you're not going to see that. But there is a tail right here, right? Because it's not perfectly abrupt. And so there is a tail, right? Even if I start off with a box, it's going to give me a line, and that's going to give me a parabola. So it's not fully self-consistent. I put in a box, and I don't get a box back. It actually is pretty close. If I plot this on a linear scale, you're going to see it's going to look like that blue line. Okay? Does that blue line look like the dotted line? I would say, for an approximation, yeah. They do. They look pretty similar. And I can still get all of the key features. But you should always remember, this line is a little bit blurred. Right? It's depletion, it's not, you never have a perfect depletion. There's a tail to it. That tail is going to be around the bilayer of that material. Make sense? Nonetheless, the depletion approximation is very, very useful, and it gets you very, very accurate results. You know, if you want 10 nines of precision, yeah, you're not going to use the depletion approximation. If you're trying to understand how something changes in temperature, or you want an order of magnitude, or even within a factor of 2, it's probably going to get you there. The depletion approximation lets you understand everything you're doing. You know, I would always do the depletion approximation assumption, and then try to do it in a more complicated way. And you can at least use it as something that you know and understand. And see, well, if I do this more carefully, how much does it change things? Okay, so I'm taking that rectangle, integrating it, getting a linear function, integrating my linear function, getting a quadratic function. And all these are starting from xd, so that's why I have xd's in my solution. Okay, so I know the potential from xd to 0 has to be phi di. So this potential at xv is xt squared minus 2xt squared plus xt squared. What is that equal to? 0. I also forced my potential to be 0 there. You know, this could have been something else, but that's what I chose as my reference. Well, what is my potential at 0? The potential at 0 is 0 minus 0 plus xt squared times q and d over 2 epsilon. Okay? So that quantity has to equal phi bi. So let's solve for xv. Bam. You know, I had something that was xt squared equals phi bi. You know, so then xt equals the square root of phi bi. This is the exact same solution that you had for an asymmetric PN diode, where one side was heavily doped, and ND would be the lightly doped side here. Okay? The maximum field, exact same expression as for an abrupt PN diode, where ND again is the lightly doped side. As my doping goes up, my depletion width goes down. Why is that? Well, because I have more charge. So I can screen over a short amount of width. But my max field goes up. As my barrier height goes up, okay, as this goes up, that's equivalent to phi bi going up, assuming my doping's kept constant. But if my barrier height goes up because I've chosen a different metal, that's equivalent to my phi bi going up if I keep my semiconductor doping the same. So then xt is going to go up because I have a larger phi bi, and my max electric field is going to go up. Okay. What is my electron concentration at 0? Well, I know what my electron concentration is in the bulk. It's just equal to ND. And I know my potential difference. Going from the bulk to the surface is phi bi. That's how much potential drop had to change. Because we're saying there's basically no potential drop on the metal side. You can convince yourself of that, right? Like if you draw this spike, just want to say, if you draw this spike and you gave this equal and opposite charge, you'll see that you could give that spike some width, but as you take that spike's width down to 0, but keep the area the same, there's no potential drop on that side. Okay, so we know what the potential is right at 0, it's phi bi. Okay, negative phi bi here. But we know we're depleting electrons, right? So I can calculate, I know what my carrier concentration is in the bulk. How much did I change my potential by? Q phi bi, or phi bi. And so I put it in this form, and that's where my carrier concentration is at the surface. This is the same thing. If phi bi was 60 millivolts, this would give me 1/10. If phi bi is 120 millivolts, this term right here would give me 1/100. Exponential of minus 60 over kT is equal to 1, or let me just take out this minus sign for a second. Exponential of 60 millivolts divided by 25 millivolts thermal temperature is equal to 10. Exponential of minus 60 millivolts over 25 millivolts is equal to 1/10. Yes, one person understands. It made a difference. But that's where it's coming from. Like, this is the equation that gives me 60 millivolts per decade. It's all the equations of this form, that exponential of something kT. When kT is room temperature, that gives me 60 millivolts per decade. When kT is 150 Kelvin, half room temperature is 300 Kelvin, then it's 30 millivolts per decade. that's just what this exponential gives me. And of course, all of this is assuming Maxwell-Boltzmann relationship. Okay? What does that mean? If we go back and look at the band diagram, it just means that we're far enough, the conduction band is far enough away from the Fermi level that Maxwell-Boltzmann statistics is valid. Okay? And the depletion approximation is valid if my carrier concentration at the surface is much, much less than the bulk. Makes sense. Otherwise, I haven't really depleted it. Which is equivalent of saying that phi vi is greater than 3 kT over Q. I think we could relax this condition, and this shouldn't be greater than, should be greater than approximately equal to. Right, because you probably don't want to be right at that limit, but you know, if you're at 5 kT over Q, like 5 kTs, that's e to the minus 5. E to the minus 5, that's pretty small, right? Something like, if we approximate E as 3, then it's like 3 to the minus 5 is, you know, 1/9 times 1/9 times 1/3. Okay. So 1/9 times 1/9 is about 1/100 times 1/3. It's like 1/300. Okay, that's my mental math. You can go on the other limit with 2's, right? And 2 to the minus 5. Let me show off to you guys. Okay, I can do that. 2 times 2 is 4. Times 2 is 8. Times 2 is 16. Times 2 again is 32. So it's already 1/32, right? So it's already, it's already, you know, much, you know, I'd say 1/32 of something is much smaller than the original. So keep that in mind. Okay, and then next class, that's a perfect ending point, we're going to talk about a current in the Schottky diode. Okay, thank you guys. I welcome any questions you have, and I will see you on Monday. Thank you.